Thank you for the introduction. So yeah, as I think Jeremy has mentioned, yeah, none of the authors could make it, and I'll be presenting on their behalf. It's an exciting work, required work for IoT devices. Hopefully I be able to convince and motivate you guys through the presentation. Yeah, so to dive in, yeah, as you're seeing on how, I guess, the IoT technologies are continuously evolving over the years, and the number of various connected IoT devices is growing fast and is expected to reach 30 billion in 2025. However, only some of these IoT devices can access the internet directly, and many other devices can only access the internet through the translation of a gateway. So we can see that they are not directly interoperable. This is because these low-power wireless radio technologies have drastically different implementation for their protocol stacks. And most of them do not directly support IP and must rely on the gateway to provide IP support. This is why there is a missing interoperability. And lack of interoperability would mean that IoT nodes without IP cannot use application layer IoT protocols. Also, service providers are bound to the IoT devices or software offered by a single provider and must stick with it. This may bring the potential risk of higher operating costs later on, as well as product functionality and stability issues. So, yeah. To overcome this problem, the research community has proposed several solutions. I think one of them is SensorNet. Some works which pay attention to interoperability among different radios. Example of which is an SP provides a unified interface to a wide range of link layer technologies that allows the network layer and above protocols to operate efficiently through link-independent optimizations. And building on top of SP, NLA proposes a modular network layer for sensor networks that ease the implementation of new protocols. And while these solutions solve for interoperability between technologies, they lack support for interoperability to the internet. And this, that is in SensorNet, end-to-end connectivity is not the primary goal, but only the interoperability among different radios that they focus on, right? And so in the IoT era, more and more heterogeneous IoT devices are connected to the internet. So researchers also try and propose many technologies to achieve interoperability to the internet. For example, 6LoWPAN is an important standard. It specifies how to format IPv6 packets in a compact way over low-power wireless links. And more technologies have been derived based on this 6LoWPAN. And an example of which is Thread, an IPv6-based mesh networking technology for 802.15.4. And many of these existing stacks in the embedded OS integrate the above technologies and are internet compatible, such as Contiki UIP and Riot GNRC. They have similar architecture as the figure is, as you can see on the figure on the right, and they provide IP, but they only provide IP per BLE and 802.15.4, right? And however these works fall short in the interoperability among different link technologies. More specifically, these stacks only provide unification above the network layer for BLE and 802.15.4, while the lower layers, as well as the LoRa stack, are still non-interoperable. So furthermore, due to their insufficient modularity, it is hard to incorporate any new protocols into these existing architectures. So, So yeah, thus there are three distinct problems that TinyNet provides solutions for. Lack of interoperability to the internet, and also the lack of interoperability among different radios. And finally, the modularity to accommodate various protocols and new and upcoming protocols. So in TinyNet, TinyNet solves for these problems by using porting IP. By porting IP that enables the interoperability to the internet, and introduces a layer 2.5 and a uniMAC interface to achieve the interoperability among different link technologies. And for insufficient modularity, TinyNet uses a modular design and a lightweight implementation. So the figure shows an overall architecture of TinyNet, and the current implementation of TinyNet unifies three different radio technologies, including 802.15.4, BLE, and LoRa. It has a modular design. And the layer 2.5 sits between the network layer and the link layer to provide unification. And it includes some key modules, which I will go over, such as neighbor management, packet relay, and so on. And so to first introduce layer 2.5 design, so what is layer 2.5, right? Layer 2.5 is an abstraction layer between the link and the network layer. It provides a unified interface to various wireless technologies. With layer 2.5, TinyNet can easily support new wireless technologies as well without too much of modification. And one of the key design of layer 2.5 involves the uniMAC. It is a key for TinyNet to incorporate many radio technologies. And TinyNet introduces two layers within uniMAC to achieve this unification. The first that you can see here is the MAC presentation layer. The MAC presentation layer describes each MAC's full functionalities. It's a thin wrapper encapsulating other MAC protocols implemented in different stacks. And there are three abstractions within the MAC presentation layer, that is property, services, and events to describe each MAC's native functionalities. So the property would mean public data or parameters which can get set or gotten by other modules, right? Services would mean the functions that can be invoked by other modules, and events describe the callback functions so that other modules can be notified of the occurrence or completion of the corresponding events. And the second is the second in the uniMAC is the MAC unification layer. TinyNet's MAC unification layer intends to present MAC-independent interfaces to upper layers. It encapsulates radio-specific functionalities and provides unified interfaces, that is uniMAC, to upper layers. And in uniMAC, some functions are direct encapsulations of the underlying layers, as you can see here, while the design of other functions requires special consideration for different radio technologies. Take the function getLinkQuality as an example here. For LPL MAC especially, link quality may be overestimated due to the inaccurate counting problem of the wake-up packets. uniMAC translates these metrics to proper link quality values for the upper layer through calibration, normalization, combination, etc. Besides uniMAC, layer 2.5 has also provided some unified services, such as common network services, support for different link technologies, and so on. The table here summarizes these relationships between the desired services and the layer 2.5 modules that provide them. So next, let's look at I want to introduce a few of the important modules of the layer 2.5 that are used for unification. And let's start with the neighbor management module, which is a key function that all previous works provide as well. It is essential for multi-hop communication. Different radios have different built-in neighbor discovery mechanisms. For example, 802.15.4 supports multi-hop communication, and it has a bidirectional neighbor discovery mechanism already. But BLE and LoRa are all single-hop communication protocols. BLE only supports directional neighbor discovery, while LoRa has no neighbor discovery mechanism at all. So therefore, it is not easy for TinyNet to provide a unified neighbor discovery mechanism. And so in order to provide fast bidirectional unified neighbor discovery, TinyNet considers two types of wireless technologies: single channel protocol and multi-channel hopping based protocol. For single channel protocol, such as 802.15.4, TinyNet reuses low power listen based neighbor discovery. And for channel hopping based protocol, TinyNet borrows the idea from BLE neighbor discovery, wherein for the BLE built-in neighbor discovery mechanism, a peripheral broadcasts packets with a default advertising period. In one advertisement duration, that is, the 3 packets are transmitted consecutively on channels 37, 38, and 39. A central device periodically performs a channel scan to receive advertising packets from potential peripherals. And when a peripheral connects to a central device, it can no longer discover other central or peripheral devices. So in order to provide bidirectional and continuous neighbor discovery services, TinyNet performs periodic scanning and adds advertisement slots based on BLE neighbor discovery. So the above approach has the following features. First, it inherits the design for BLE and thus can reuse a portion of code in its neighbor discovery module. that's already out there. And second, it enhances the original BLE neighbor discovery in the sense that an ordinary node can discover neighboring nodes, and it can also be discovered by other nodes. At the same time, it is also compatible with the original BLE neighbor discovery mechanism. And finally, it works for both BLE and LoRaWAN with different configurations. And it's worth emphasizing that users can change the neighbor discovery algorithm easily due to the modular design principle of TinyNet. Next, I'll describe a bit about the packet relay module. The packet relay module is important for enabling multi-hop wireless routing. For 802.15.4 radio, packet relay is relatively simple since it uses a single channel. For BLE and LoRaWAN, however, there is no direct support for packet relaying since both radios are originally targeted for single-hop communication services. For channel hopping protocol, it is necessary to allocate reception slots and synchronize transmission reception behaviors between the sender and the receiver. TinyNet employs an automatic synchronization approach to achieve this. TinyNet automatically allocates the reception slots when the downstream nodes perform channel scan and the relay node performs advertising. The downstream nodes can request one or more transmission slots, and the relay node coordinates the allocation and confirms the final decisions to the downstream nodes. And next, the third module is the communication scheduling. It is responsible for buffer management and packet scheduling. For an IoT node with N radios, N packet queues are required. It is possible that a packet will be transmitted on multiple radios as well. TinyNet provides different scheduling mechanisms for the different numbers of radios. For the single radio stack, TinyNet provides FIFO packet scheduling and priority-based packet scheduling. And for multi-radio platforms, TinyNet provides a unique config graph-based packet scheduling approach to avoid transmitting on the same ISM band. In the conflict graph, a node represents different channels of each radio, and an edge between a pair of nodes represents a conflict in between them. And when a packet is to be transmitted, TinyNet first determines which radio it should be transmitted to based on the conflict graph. There are further details for the other modules in the layer 2.5 and uniMAC in the paper. And I think for now, I'll go into the implementation of TinyNet. And to evaluate TinyNet, it is implemented on Contiki OS 3.2 and Riot OS, adding 1,500 lines of code and 2,600 lines of code, respectively, in each of the OSs. TinyNet is implemented on CC2650 and Heltec IoT LoRa nodes. And the authors have also built a gateway comprising of a Raspberry Pi 3 connected with 2 CC2650 chips and 1 Heltec IoT LoRa chip. And layer 2.5 and the above layers run on the Raspberry Pi, and the link layer and the lower layers run on the radio devices. RPi and the radio devices are communicated by serial line internet protocol. And for the testbed, TinyNet mainly uses a mixed indoor and outdoor testbed for the evaluation. The gateway node is deployed in the laboratory. 6 LoRa nodes are deployed outdoor in a 500 meter by 1500 meter area, and 6 BLE and 6 802.15.4 nodes are deployed indoors. So TinyNet enables the interoperability to the internet, which is demonstrated with 2 case studies here. In the first case study on the left, BLE and ZigBee nodes communicate with each other by TCP with TinyNet, where we see the round trip time is roughly 275.2 milliseconds. And the second is RESTful API over CoAP. In this case, with TinyNet, a laptop can turn on or off an LED on C62650 across a gateway, and as long as the IoT node implements and exposes the RESTful API. And for which we actually see a round trip time of roughly 242.1 millisecond. So TinyNet also enables interoperability among different link technologies, and the end-to-end delay of TinyNet in different scenarios is tested, and for which the results are as shown in the figure. And we can see that irrespective of, as we add more relays, and it can still enable interoperability with minimal latency overhead. Besides, as shown in the table, various existing protocols can be composed of the modules provided by TinyNet, such as RPL over BLE, RPL over LoRa, rateless BLE, and so on. The authors measure rateless of BLE and RPL over LoRaWAN in terms of packet reception ratio and end-to-end delay, respectively. And the results show that RPL over LoRaWAN can significantly increase the PDR compared with default LoRaWAN, where we can see that compared with the original BLE, the rateless BLE reduces transmission delays. Additionally, the code size and memory footprint of TinyNet was measured when realizing RPL over BLE and 15.46 LP with BLE6 low pan, and the results are as shown in the figure. For the protocol for single radios on the left, that is RPL over BLE, the TinyNet has comparable code size and memory footprint. For protocol over multiple radios, that is 15.46 low pan with BLE low pan, TinyNet has a significant reduction of up to 39 to 45% less code size and 10 to 64% less memory footprint. And we all know that low power is very important for IoT devices, right? And so here are the measurements for the energy efficiency of TinyNet across different protocols. And where we can see that TinyNet, Tencent Stack, and Riot GNRC result in similar radio duty cycles. And in a few cases, TinyNet has a slightly larger duty cycle due to additional functionalities like bidirectional neighbor discovery, but it still has low power performance overall. So before concluding, let's reemphasize how TinyNet differs from existing work. Compared with vertically integrated architecture and existing internet-compatible architectures, TinyNet designs a layer 2.5 that works on many different radio technologies. TinyNet has more modules at layer 2.5 and has drastically different designs compared with existing works. Besides, TinyNet adopts a modular approach to provide a different set of modules supporting key services. And unlike TinyOS's static approach and compile time wiring, TinyNet makes use of pointers and dynamic memory allocations, allowing addition of more advanced features in the future, such as dynamic loading of the modules. In conclusion, in this paper, we propose TinyNet, a lightweight, modular, and unified network architecture for IoT. Compared with existing stacks, TinyNet achieves smaller code size and memory footprint and comparable energy consumption. TinyNet could allow interoperability among heterogeneous radio technologies and simplify new protocol design by module composition. Thank you, and I think we have GMA on Zoom to answer your questions, and you can also reach out to Wei at the email address shown. Thank you.